All right, welcome. In this video, we're going to talk through some acid-base problems that we can use to review for an upcoming assessment. And the first set of problems we're going to look at are ones related to the idea of conjugate acid-base pairs and think about that Bronsted-Lowry definition, and then just some general things about pH. So first thing you want to be able to do is think about what it means to be an acid or base and identify conjugate pairs. So we want to remember that our definition of an acid is a hydrogen giver, and then a base is a hydrogen taker. And sometimes we refer to that hydrogen ion as being a proton. So we might use the term proton giver, proton donor, or proton taker or acceptor. And so we have to look at these reactions and figure out what's going on. There's always going to be one hydrogen ion transferring from one substance to another substance. It looks like in this first reaction that my H2CO3 is giving a hydrogen to my H2O. And so we would refer to my H2CO3 as the acid because it's the hydrogen giver. Water is behaving, started writing water underneath it. Water is being the hydrogen taker, so it's acting as the base. And then the idea of a conjugate pair, the conjugate is what is left over after your substance either gives or takes a hydrogen. So let me kind of try and highlight my conjugates here. So if this is my acid, right here, this would be the conjugate base. So H2CO3 and H2O3 minus are a conjugate acid-base pair. And then H2O is a base, H3O plus is the conjugate acid of that base. So let's look at this next one. NH3 is looking like it's turning into NH4. So NH3 is behaving as a hydrogen taker. It's taking a hydrogen from water. So that means NH3 is acting as a base. And that means NH4 is its conjugate acid. So that's one conjugate pair right there. And then water is being a hydrogen giver. So it is acting as an acid. And then what is left behind after it gives up a hydrogen is its conjugate base. There we go. And here's a good time to just mention the idea of, we were thinking about conjugate pairs, is there's this saying like weak pairs with weak. So the conjugate of a weak acid is a weak base, and then strong pairs with neutral. So notice how in this case, like H2CO3 is a weak acid. I know that because it's not one of the 6 strong acids I memorized. And therefore, its conjugate base right here, HCO3 minus, that must be a weak base. So the conjugate of a weak acid is a weak base. And then NH3 is a base. It is a weak base because it's not one of my strong bases that I memorized. And so the conjugate of a weak base is going to be a weak acid. So NH4 plus is a weak acid. And then if we look at an opposite, like water is acting as an acid, but we know that water has a pH of 7. It's neutral. So the conjugate of something neutral is going to be strong. So notice how its conjugate base is hydroxide. So that's about as strong a base as you can get, right? It's just pure hydroxide. So the conjugate of neutral is going to be strong. So weak pairs with weak, strong pairs with neutral, general rule of thumb there. Okay, so let's look at this one. In this case, it looks like HNO3 is giving a hydrogen to water. So HNO3 is the acid. And HNO3 is one of my strong acids. So its conjugate base over here, NO3 minus, is actually going to be neutral. Applying that rule we just discussed there, the conjugate of a strong acid is going to be neutral. And then in this instant, it looks as though water is being a hydrogen taker. So water is acting as a base here. So its conjugate acid is right here. And the other thing you want to notice here is that water can either be a hydrogen giver or taker depending on who it's paired with, right? So in some of these, it's acting as the base, and some of it's acting as the acid. All right, and last one real quick. This one looks like it's being a hydrogen taker, so this is a base, and this right here is its conjugate acid, and that means my water is acting as the acid. It's giving away a hydrogen and leaving behind OH, which is its conjugate base. Okay, so now let's look at just kind of trying to find the conjugate base for each of these acids. So remember, the conjugate base is what's left behind when an acid gives away a hydrogen. So to find the conjugate base, all you do is you take away a hydrogen ion. So HNO2 becomes NO2, and now it's got a negative charge because you removed a positive thing. H2SO4, its conjugate base is HSO4. You only ever give or take one hydrogen when you're looking at these kind of conjugate pairs. And then HF, its conjugate is F minus. And we're looking at the conjugate acid, that would be the opposites. When you add a hydrogen, you get the conjugate acid. So NH3 is a base, its conjugate acid is NH4 with a plus charge. Because remember, this hydrogen has a charge associated with it. So you just have to think about the charge on these ones. ClO becomes HClO. And now it's neutral. It went from -1, now it's neutral. CO3 2 minus becomes HCO3, and now it's got a -1 charge because we had two negatives and then we added a positive, so it adds up to -1. All right, so be careful with charge. The other piece here of this objective is thinking about some general knowledge about pH. So I'm going to scroll out over here and take a look at our equation sheet. And we're going to be applying some of these equations like down here. It's like, what is pH? Here we go, that's defined right here. There's a relationship between pH and pOH and this thing called Kw. So let's take a look at this first question. A solution of an acid has a pH of 3.15. What is the H plus concentration? Well, this relationship tells us that we know that pH is the negative log of the H plus concentration. If we were to do the inverse of this, and we want to rearrange this, do some kind of algebra here, and solve for H plus, we will find that the H plus is 10 to the minus pH. So that's what we're going to do here. Is we're going to go, the H plus is going to be 10 to the minus pH. And then I'm doing this live here, so I'm plugging this in my calculator. Make sure you practice plugging these into your calculator. So each calculator is different. You want to know how this works. So I get 7.1 times, let's see, 10 to the -4 molar. So this is the concentration, so it's in molarity. That is my hydrogen ion concentration. If you want to write it in standard notation, it would be 0.00071. And I rounded it to 2 sig figs because the way that logs work, when you're seeing a log value like pH or pOH, it's only the digits to the right of the decimal that are significant. So when I write 3.15, that just has 2 sig figs. So I'm going to report my molarity with 2 sig figs. All right, and I'm going to calculate the OH. And there's a couple ways you could do this. I could use this relationship. H plus times OH is 1 times 10 to the -14. So now that I know H plus, I can solve for OH minus. Or another option I can do is I could calculate pOH first, and I'm actually going to do that. So I know that my pH plus my pOH is 14. That's this relationship right here. So to find pOH, I'm going to take 14 minus my pH. And I'm going to assume that this 14 has like an infinite number of sig figs there. So my answer is still going to have 2 sig figs in it, if you're curious about my sig fig steps here. So that's the pOH is 10.85. And then I'm going to go up here, calculate the OH. Well, the relationship between OH and pOH is the same as like the relationship between H and pH. So if I want to find the hydroxide concentration, I can go 10 to the minus pOH. So that'd be 10 to the minus 10.85. And I'm going to plug that in my calculator. That would give me 1.4 times 10 to the -11 molar. All right, so let's check out this one. So here's a base. We've got a base and it's got a pH of 11.2. And we want to find the, whoops, I miswrote one of these ones. I should have called this pOH. All right, so we know the pH is 11.2. Let's actually, I don't know why I put these in a different order. I don't know why I did that, but let's find the H plus first. Okay, so let's find the H plus. It doesn't really matter what order you do these things in. H plus is 10 to the minus pH. So it's 10 to the minus 11.2. All right, so 11.2. And then you do actually have to solve this. You can't just leave it, this is your final answer. You have to plug in your calculator and solve. And you end up with 6.3 times 10 to the -12 molar. That's the hydrogen ion concentration. Notice it's a base, so it's got a lot less hydrogen ions. And then let's find the pOH next. So I know that pH plus pOH adds up to 14. So that means my pOH is going to be 14 minus, 11.2. And we're going to have that still with, 2 sig figs there. So my pOH is 2.8. So to find the hydroxide concentration, it's 10 to the minus pOH. So 10 to the minus 2.8. I plug that in my calculator. And again, make sure you're actually practicing doing this. Don't just watch me plug in my calculator. You need to know how to plug into your calculator correctly so that you can solve these problems. All right, so there you go. So just some basic kind of pH, pOH relationships using these on your equation sheet. Again, you're given these, you don't have to memorize them. And then if we look at number 6, we're trying to find what is the pH of this solution. So these are examples of strong acids and strong bases. So you want to know your list of strong acids and strong bases. You can go back and look at that it's either on the first or second page. It might be in both places. In your acid base folder, Unit 8 gives you a list of those strong acids and bases. There's a reading that goes over those. But the main ones to be aware of they're these halogen ones like HCl, HBr, HI. HF is not on this list. It's the only halogen that's not a strong acid. The other main ones to know are nitric and sulfuric. And then this less common one you might run into is I think that's perchloric is the name of it. So HCl, definitely a strong acid. So that means if you have 0.0, that means this. So when you stick HCl in water, it's going to totally break apart into H plus and Cl minus ions. So that means if you have a 0.02 molar concentration of HCl, really what you have is 0.02 molar H plus ions and 0.02 molar Cl minus ions. Cl minus ions aren't impacting our pH at all. It's this that this is gonna affect the pH. So we know pH is the negative log of the hydrogen ion concentration. So pH is the negative log of 0.02 molar. And if you plug that in your calculator, 0.02, take the log of it, you get the pH is 1.699. So I'm going to round it to 1.70 to give me 2 sig figs there. So there you go. Now let's take a look at it for a base. So for a base, we've got my strong bases are my alkali metal, so like NaOH, LiOH, alkali metal hydroxides, and also some of the heavier alkaline earth metals. So basically like my first 2 columns on the periodic table. These are what we consider our strong bases. So they're all ionic compounds that contain hydroxide. So when they go in water, they're going to completely split apart into these ions. So if I've got 0.15 molar sodium hydroxide, really what I have in solution is 0.15 molar sodium ions and 0.15 molar hydroxide ions. The sodium ions do not impact my pH. It's just the hydroxide that does. So with the bases, what I'm going to find first, I'm going to find my pOH first. So my pOH is my negative log of my hydroxide concentrations, the negative log of 0.15, and that gives me 0.82. But the question asked me for pH, and what I have right now is the pOH. So I got to do this next step using this relationship. pH plus pOH is 14. So to find the pH, I'm going to do 14 minus the pOH here. And so it's 13.18. And I'm rounding those all to 2 sig figs there. And because again, remember when you're doing log values, it's the digits to the right of the decimal that are significant. So that's with 2 sig figs. All right, so I'll make a separate video for the other parts of this practice set. So that's it for part 1. Thanks for watching.